are just in the process of discussing the various options you have for Bell test experiments, and I was just giving a brief overview of what are the options of even just producing these singlet states. And for example, we mentioned scattering of particles, or just taking the electrons out of an helium atom, or then the more relevant options like parametric down conversion, for example, or photons emitted from a cascade in an atom. And I want to conclude this brief overview by just pointing out qubits, because nowadays you have these artificial quantum systems that can be fabricated with the desired parameters, and you can tune the parameters even in situ in the experiment, and you can then apply pulses to these qubits and manipulate them at will and provide interactions between the qubits, so you have all the flexibility. And among the many, many possible things you can do, in particular, obviously you can produce an entangled state. I mean, if you have a qubit setup where you wouldn't be able to produce an entangled state, it would be a very bad qubit setup indeed. So let me just briefly mention the options here. Okay, so the point about qubits is that in contrast to all the other examples we have mentioned, you have full control. You can easily manipulate them, you can easily read them out, because that is part of the definition of what is a good qubit. And I'll just mention two examples. One of the examples would be ions, that is charged atoms in a trap. And if you place two of them inside a trap, and you choose them such that they have spin 1/2, then there are ways to manipulate them such that you create an entangled state. Another example I want to mention are superconducting qubits. So if you design an electrical circuit and cool it to sufficiently low temperatures, then it will often go superconducting, and then you could have structures such as the one I'm drawing right now. So you would have two qubits, which are basically just metallic boxes that are cut in two halves, and then Cooper pairs will be able to tunnel between the two halves, and this, under the right conditions, can then be a two-level system. And if you have two of these superconducting qubits and, for example, couple them via a metallic strip that is a resonator for microwaves, then again you have a situation where you can actually very easily engineer entangled states of the qubits. And then there are just very many other examples where you can, for example, you can have electron spins and quantum dots, or you can have the excitations and excitonic quantum dots, and many other examples. Now, let me just briefly mention how you would go about creating an entangled state. For example, in such a situation, you can easily have an effective coupling between the two qubits that is mediated by this microwave resonator, and the Hamiltonian for this effective coupling would contain an interaction term that goes like, for example, sigma x1 times sigma x2, where 1 and 2 refer to the two qubits. And so what that does is, for example, if you have an excitation in qubit 1 and no excitation in qubit 2, then applying this Hamiltonian will just flip the excitation to the other qubit. Now this in itself, after you flip the excitation to the other qubit, that wouldn't be an entangled state. But let's see, so the interaction, as I said, can take up-down, that is excited ground state, into the down-up state. And the point is that in these circuits you can easily switch the interactions, or at least switch on and off effectively the interaction. For example, this interaction will be effective only if the two qubits are resonant, because only then is a process that conserves the energy of the original Hamiltonian. And so just by tuning them in and out of resonance with each other, you can effectively make this process happen or not. And so in particular, that means you can switch on this process for only a given amount of time. So you start in this state, which is obviously a product state between up and down, and then you switch on the interaction only for a given amount of time, and if you choose the time correctly, then you will end up in a superposition of the two states. So you would have first, say, started in the ground state of both qubits, then excited the first qubit, and then switch on the interaction and wait for a sufficient amount of time. And so then you could end up in a state like the following, that is a coherent superposition of up, down, and down, up. And it would be a little exercise to show that if that is the Hamiltonian and you switch it on for the correct time, then indeed there would be a phase factor in here, but for our purposes this is trivial. This is still a maximally entangled state, and so this is good enough for a Bell test. And anyway, you could get rid of this phase factor in principle by doing a single qubit operation on, say, the second qubit. Okay, so that is one option. And now, sometimes the interaction Hamiltonian looks different. For example, in other situations, one could have an interaction Hamiltonian that goes like sigma z times sigma z. Well, that is another option. That depends on the physical situation. And still, you will usually find a way to exploit any such interaction to create entangled states. And just for this example, you could, for example, start with both qubits in the ground state. Then I will draw an energy level diagram where, say, one of the qubits is in the excited state or the other qubit is in the excited state. And in addition, there will be the energy level where both qubits are actually in the excited state. But what I want to point out by drawing this dashed line is that this state does not just have twice the energy of one excitation. And the reason is that I do have this interaction term in the Hamiltonian. And so you can exploit this because now you can irradiate your two-qubit system by radiation. For example, in the case of superconducting qubits, it would be microwave radiation. That will easily flip one of the qubits, but then you are not in resonance anymore with the two-qubit excited state, and so you won't go there. And so if you switch on this radiation for the correct amount of time, what you can end up in is just a coherent superposition of up, down, and down, up. But you won't flip all the way up to the up, up state. Yeah. If this level were in resonance with the radiation, actually you would never end up in an entangled state, you would always remain in a product state. So that's a little exercise to show, because that's the situation you have if there is no interaction between the qubits. And if you just irradiate two atoms or two qubits with radiation that is resonant with the individual transition, you just get a product state. You can never get an entangled state if there is no interaction. Okay, so that would be a way of producing an entangled state. Okay, fine. Now I've given this overview, and the idea was just to show that there are many different options. I want to go back to tell you something about the history of the actual experiments that were done. And there I want to go a little bit more into the details of what were the actual numbers, what were the actual efficiencies achieved, Because that's the whole point of the story, that you don't just appeal to Gedanken experiments, which you can always write down on paper, but that you do and compare with actual experiments. And so it's really important to be aware of the non-idealities that are there, because in the worst case, they could indicate that there's something fundamental we are missing, for example. That doesn't seem to be the case, but at least you have to look very closely at the experiments to see that even though they deviate from the ideal Bell experiment, probably they still indicate that quantum mechanics is fine and local hidden variables are ruled out. Okay, so I'll just mention briefly what I already mentioned, that for example you can have this positronium decay that was studied by Wu and Shaknov in 1950 and then again in the 70s after Bell's inequalities were known. Also there's the issue of proton-proton scattering, so I could group all of those as high energy experiments. The only trouble with them is that usually they are very, very far from the ideal situation. For example, it's really hard to find out about the polarization of these photons that you produce in positronium decay, and actually it works by yet another scattering process, by a Compton scattering process. And so these are very far from the ideal situations. Okay, now the first experiment I really want to discuss in some more detail is the first ever Bell test done with this atomic cascade principle. That is, you have an atom in a highly excited state and it's arranged such that it quickly emits two photons, one after the other. And that experiment was done in 1972 by Friedman and Clauser. And so what they used was a calcium atom. And let me just draw the level scheme that was used in this experiment. Now, I already told you the basic principle is I should have one excited state and then several intermediate states and one ground state, such that photons can take different transition pathways through these several intermediate states. Now this scheme involves one more level, which is just used to provide the initial excitation. So let me just draw the level scheme. Now, these lower three levels are the levels we've been talking about, and what I don't draw here is the fact that this intermediate level is degenerate in the sense that we already discussed, because it's a p level which has several possible projections of the angular momentum. The upper level is just an S state, and in the same way the lower level is an S state. Whereas the intermediate level, as I said, is a p state. Now, calcium has two electrons in the outer shell, so to speak. And so you want to indicate in these levels what these two electrons are doing. And here, for example, both of them are in a 4p orbital. Here, both of them are in a 4s orbital. And here, there is one of them in the 4p and the other in 4s. Okay, so whenever people write down these atomic level schemes, this big letter is just used to indicate the angular momentum. So, for example, this is just the total angular momentum 0. Then you would write something to indicate the total spin. And instead of just writing down the total spin, they indicate 2s plus 1, yeah, which is the multiplicity. Which means if 2s plus 1 is 1, the total spin is 0. And they also indicate the total angular momentum. That is how spin and orbital angular momentum combine into total angular momentum. And that would be 0 here, 0 down here, and 1 here. So in other words, the spin is always 0. The electron spin is always 0. The combined electron spin is always a singlet state. And all that happens is really the orbital angular momentum changes. And so then the transition we are interested in is the two-photon transition where I first go down here, emit a first photon, gamma 1, and then go down one further step and emit a second photon, gamma 2. Okay, and since there are electron interactions, these two can have different energies. Now, why do I need this upper state, which happens to be 3d 4p p? Well, that's used to excite the whole system. So what really happens is you might use a laser. At the time, they didn't even use a laser. And then you excite this upper state, then you fall down in the first transition to the initial state of our scheme, and then you quickly in succession have these two photons emitted. And these photons are emitted within a time of only about 5 nanoseconds, so that's the lifetime of this intermediate state, which means when you finally register the clicks, it's just click, click within 5 nanoseconds. So that's important to know because that means you get your two photons in coincidence within this time interval. Okay, so what they did in addition to having this level scheme is they used frequency filters to select for gamma 1 or gamma 2. So on one side you want gamma 1, on the other side you want gamma 2. And then they used polarization filters, obviously, for the Bell test. In that experiment, they used really just polarization filters in the sense that one polarization is transmitted and the other polarization is simply absorbed. This is not quite the ideal case. In the ideal case, you would want to have the situation where, say, one polarization is detected by one detector, the other polarization is detected by another detector. Because if the detectors are not ideal and you don't know when such a pair is emitted, it's hard to tell whether non-detection means just it was the other polarization, or it just means there was nothing, or it just means that the detector didn't click. Okay, so schematically, we will draw the situation like this. Here you have your filter, and then if the photon passes the filter, it can be detected by the detector. So that's a little downside of this particular experiment. Only one polarization direction is detected. And the overall detection efficiency or collection efficiency is quite low because you have this situation where you emit photons like this, and then they have to go into the detector, but if the solid angle that is detected is rather small, then the overall number of photons that happen to fall on the detector is also small. And in addition, of course, these detectors have finite efficiency. So it turns out that the probability for, say, this photon to be detected at the detector was only 10 to the minus 3 in this experiment. So that means if you emit one pair, then the probability to actually register both of the photons is 10 to the minus 6. Now, why would you want to collect only these back-to-back photon pairs, so they would fall on a lens and then go into the detection equipment? The reason is that if you also look into other directions, then the polarizations, as you can imagine, the polarizations look different, simply because we have dipole radiation and the polarization has to be orthogonal to the propagation direction. And so if you have a relatively large angle here, you will collect all these different polarizations, and that actually happens to decrease the correlations you see between the polarizations. So that's a downside of the experiment. So they had to have a compromise between wanting to increase the collection angle in order to get more of the pairs detected, and having to decrease it in order to get a high polarization correlation. So that was one downside. Okay. Now, all told, when they were running this experiment, they saw a coincidence rate, that is, detected pairs of about 0.1 Hertz. So every 10 seconds, essentially, they detected one pair. And you have to compare this against the accidental coincidence rate, because actually the detectors at the time, and also modern detectors, have a dark count rate. So even if, in principle, there's no light hitting the detectors, they will sometimes click. And there is a challenge there, because if that dark count rate is too large, it will just give you accidental coincidences. And so it turns out that in their experiment, these accidental coincidences were at least lower than the systematic coincidence rate that you wanted to detect. So that was about 10 times lower. Because it turns out that the dark count rate was about 100 Hertz, but then of course, once you register one event, the probability to register another event within a 5 nanoseconds time window, even if there's a 100 Hertz dark count rate, is relatively low. So that was the trick. So it was really crucial to have this small coincidence window. Okay, and this was quite a heroic experiment, it must be said, because in order to get good statistics in spite of this one pair per 10 seconds rate, they needed to run the experiment for 200 hours. Nevertheless, it paid off because, at least after accounting for all the inefficiencies, they found A, it agreed perfectly with the quantum mechanical expectation for these correlations, and B, again, accounting for those inefficiencies, it violates the Bell's inequality and rules out local hidden variable theories. We will still have to discuss what it means to account for these inefficiencies, because there's some loopholes involved there. Essentially, it means you assume that even though you detect only such a small fraction of the emitted pairs, they give a fair sample of all the pairs that are emitted, and you don't have some biased sample. That means if you were to include all the pairs, you would get other statistics that you have to exclude somehow. Okay, so it then turned out there were other experiments being conducted slightly later, right, around the same time, and at least one of the experiments was in contradiction with quantum mechanics. But it turns out that later people found out that quite likely this was because somehow the glass bulb holding the vapor had become somehow birefringent and spoiled the polarization correlations. So you see that you have to look into even the tiniest detail. At the time, I guess it was quite exciting to have these different outcomes of the different experiments. Okay. So that was the status in the 70s. Now, there are ways to improve this experiment. One of the possible improvements, as I already mentioned, is that instead of only detecting one of the polarizations and completely throwing away the other polarization, you want to be able to detect both of them. And the other desirable thing would be to increase the efficiency of the detectors, for example. And yet another very important point is that this experiment did not really try to quickly change the detector settings. And we know that if we allow for communication between the two detector stations, we can always have correlations, even mimicking the quantum mechanical correlations. So we want to make sure that there are no such communication, that there is no such communication going on, and for this purpose we would want to switch the detector settings very rapidly. So at least two of these desirable features were then really implemented at the beginning of the 1980s in a series of experiments done by Alan Espy and his co-workers. And that's quite a famous series of experiments. So again, they used the calcium cascade. But in contrast to the Friedmann-Clauser experiment, they were the first to actually have both polarizations detected. And in another subsequent experiment, they were also the first to actually switch rapidly between the detector settings. And this second point I want to discuss in some more detail because it's really interesting. Now, and that was the experiment done in 1982. Now, how do you rapidly switch the settings? I mean, you could of course rotate the polarizer, but that is just too slow. So their idea was just to keep the polarizer fixed, but really have two different polarizers with different angles, and then quickly direct the light beam either to one or the other polarization filter. And the question is, how do you do that in a quick fashion? And they had a very ingenious answer. They used Bragg reflection from a standing sound wave in water, and then depending on the current amplitude of the sound wave, either you get a lot of Bragg reflection or you don't get any Bragg reflection. So this was their very fast switch. So let me draw this. Here you have a tank of water, and then you have a standing ultrasound wave, such that the wavelength matches, is commensurate with the wavelength of light. And so that means if you have a light beam coming in, either say it's not Bragg reflected, because for example the amplitude of the sound wave happens to be 0 in that moment, or it is Bragg reflected. And so since the standing wave oscillates at 50 megahertz, what they essentially implemented was periodically switched Bragg reflection at 50 megahertz. More precisely, I guess the intensities were modulated with a cosine function, but the cosine function has the tendency of staying for a very long time near the minimum and the maximum. And so then after this Bragg reflection, you have two paths, each with their own polarization filter that has been set to some setting. So it has to be admitted this is not a completely random switching, it's periodic switching, but at least they used a different period for the two different detection stations. And so since these periods are incommensurate, basically it's practically like random, at least within the abilities that they had at the time. Now, how fast do you actually have to switch the detector settings? What do you want to achieve? And in order to understand this, let us just draw a space-time diagram that represents the full situation and represents the possible light signals that could travel between the detector stations. Okay, so at some point you have the emission of the photons from your atomic cascade, and we know that there may be about 5 nanoseconds delay between the two emission events. So this is not completely certain when they are emitted. Then they run to the detector stations. And then you have to set the setting, have the photon go through the filter and detect it, and then record the detection event. So all of that takes some time, like for example this here, or this. So these are the intervals between deciding to set the setting and final detection. And what you want to make sure is that the signals that could, in principle, emanate from detector station A in order to tell about the setting, that these light signals will actually not arrive at detector station B until way after the detection process has been completed. So if this light signal arrives here at B only way after the detection process has been completed, then this cannot have been influenced by what has been going on at A, and same for light signals going between B and A. Okay. So that is the basic idea, and what people say for such a situation is they say that the two detection events, or rather detection intervals, are space-like separated. Now, how do the numbers add up for this particular situation? As I said, there is about 5 nanoseconds uncertainty in the two emission events, and then it turns out that the effective detection interval happens to be around 10 nanoseconds. So what you should compare is the travel time of light between the detector stations with the 10 nanoseconds. And so for the distance they used, the travel time was about 40 nanoseconds, which is larger than the 10 nanoseconds. Not by a large degree, admittedly, but at least it's larger. So that would be L. So these several meters were enough to guarantee in principle that no light signal could reach the other detector station in time to reveal the setting. Okay. So this was really the first experiment ever that cared about this. Now what they found is that they still could violate Bell's inequality. There was no deviation from quantum mechanics, so this was all fine. Now that was basically the last of the atomic cascade experiments, and then as the 1980s developed, they introduced these parametric down-conversion sources, which were more efficient. So let me just discuss this. So in the middle of the 80s, there were several experiments done by people such as Allais and Xi, Hong, Wu and Mangel and co-workers. And let me just draw a typical setup. So you would have one of those nonlinear crystals that we discussed, where you can split one photon into two. You would have light coming in and being split into two photons that emanate from this crystal. But the type of parametric down conversion they've used at first in those experiments is a type of parametric down conversion where the two polarizations are actually identical. And it's called type 1 parametric down conversion. Now, this seems to be a little bit boring because that is not an entangled state. H is just a product state. So let me tell you about the trick that they used, because it represents some of the interesting tricks that people applied in this field. Now, you can rotate the polarization such that it becomes vertical. Still, this is not an entangled state. Then you reflect these beams from mirrors and let them go through a beam splitter. Now what happens at this beam splitter? So you have just two beams, their polarizations are in a product state. The upper beam is definitely horizontally polarized, the lower beam is definitely vertically polarized. What happens at this beam splitter is the following. Let us write down the wave function of these two photons after the beam splitter. Now, take the upper photon, it might go into the upper path, provided it's reflected. And so I will denote that by 1h, which means there's a photon in path number 1 with horizontal polarization. And the prefactor will be the amplitude to be reflected from this beam splitter. Plus, there's a possibility that it's just transmitted, again with horizontal polarization. So it will end up in beam number 2, and I denote that as 2 with subscript h, again to indicate that it keeps its horizontal polarization. Now this is one part of the wave function, but there's another part of the wave function, and that's the one for the vertically polarized photon that comes in. And so again, what can happen is it can be reflected and end up in beam number 2. Or it can be transmitted and end up in beam number 1. So these are the possibilities. And now if you look at this state, it's of course still a product state. But now you can expand this wave function, and there are several terms, but we will now keep only those terms where exactly one of the photons is in beam number 1 and the other photon is in beam number 2. There are also the other cases where, say, both photons happen to go into beam number 1. But at least in principle, we can distinguish those cases, because if we place detectors up here and down there, then only if both the upper and the lower detector click do we have a state where obviously one photon went along direction 1 and the other along direction 2. So that's the idea. Let me just write down those terms. For example, I have this first term where both have been reflected, and then there's one photon horizontally polarized in beam 1 and another photon vertically polarized in beam 2, plus the other term when both of them have been transmitted, and then one of them is horizontally polarized but now in 2, and the other is vertically polarized but now in beam number 1. And so if you just select those events where both detectors click in 1 and 2, then you select only this part of the wave function. And because of that, if you just focus on this part of the wave function, and if you assume, say, it's a 50-50 beam splitter, so that the magnitude of r squared is equal to the magnitude of t squared, it's really an entangled state. And so there is a name for this. You say, I post-select only those events. Now, I just care about the events where both of the detectors have clicked. And then if I study the correlations for just those events, these are the correlations predicted by that part of the wave function. Okay, so that's a neat trick, but, and in principle, logically speaking, it's okay if we think about it, but conceptually maybe it's not as tidy as the ideal experiment. Things changed in 1995 when the Zeilinger group introduced a really nice new, very high efficient parametric down-conversion source that completely did away with the need for such tricks. And the idea was to use a different kind of parametric down conversion, so-called type 2 parametric down conversion, which happens to have the property that the two beams that are emitted have different polarization, one horizontal, the other vertical. So let me draw this. So you can find the paper, and I linked to it on the web page, that's Kwiat et al. From the Zeilinger group. So I just draw the source here. Again, you have an incoming beam. You have your nonlinear crystal. And then the horizontal and the vertical photon happen to be emitted on cones. And so I want to draw them carefully. So this is one of the cones. That is the other cone. And those cones happen to intersect. So what I'm drawing here is the possible directions of light of a given frequency. If you look at other frequencies, they would be emitted into other frequencies, into other directions as well, but you could place a frequency filter here, for example, and then you would see this picture. So the upper cone, say, is horizontally polarized, the lower cone is vertically polarized. polarized. And now the idea is that these photons always come in pairs. And for example, if I were to detect a photon up here, horizontally polarized, then I will also detect a photon down here, vertically polarized. Now that situation is still boring, because then I still know for sure that this is horizontally polarized, that is vertically polarized, and I have to do the beam splitter trick. Yeah? Because it's not really different than the situation I had after rotating the polarization. But there's a trick to go at the intersection of the cones. Because then if you choose only these two directions, like let's call them 1 and 2, you don't really know if you detect a photon at 1, is it horizontally or vertically polarized. The only thing you know is that the other photon will have another polarization. So that's the trick. So if I write down the wave function for the photons only along these particular two directions and concentrate only on the polarization part, then the wave function is really an entangled state automatically. And it would look like this, for example, horizontal along direction 1, vertical as a polarization for photons in direction 2, plus the opposite. And in principle, there can be a phase factor between the two, depending on the details of the crystal and so on, but that's fixed. Okay, so that's the entangled state, and that's good enough. That's a maximally entangled state, and you can use it for relativists without any post-selection. And so, with this new source, they really had a much higher rate of pairs. And so their coincidence rate was rather kilohertz. And because of these high rates, you don't have to wait very long to get very good statistics. And if you get very good statistics and you agree with quantum mechanics and you insert into Bell's inequalities, you remember quantum mechanics would predict 2 times square root of 2 for this combination of correlators, and local hidden variable theories predict the value of 2. And then if you are close to the quantum mechanical prediction, you very quickly deviate very strongly from the local hidden variable bound. And the way people express this is in terms of standard deviations. So you say, how large is my remaining statistical uncertainty, because I only have a finite number of samples, and you compare the deviation from the bound with the standard deviation. And so for them, after 5 minutes, they could boast about 100 standard deviations, deviation from the local hidden variable bound. And so for comparison, in this old Friedmann-Clauser experiment, it was only a few standard deviations, despite the 200 hours running. For example, also, of course, detectors used here were probably a bit more efficient than those used by Friedmann and Clauser. The detector efficiency here, as far as I could find out, was about 10% or a bit more than 10%. Now, this is already very nice because it's such a much more efficient source, and it's also more robust than schemes that require this extra trick. But in principle, conceptually, this did not yet introduce anything new. And so what was then really new was in 1998, an experiment also by the Zeilinger group, where they used this kind of highly efficient source to again reconsider the space-like separation of the detectors, just like in the ASP experiment, but they really did the random choice of detector settings. So that is an experiment that I definitely want to discuss after I've cleaned the blackboard. Okay, so that is the 1998 experiment by the Zeilinger group, and you'll find it under Weiss et al. So that is practically the ideal experiment to provide these locality conditions, the space-like separation. In particular with an independent random switching of the settings. Okay, so here's the setup. You have the source, you have the photons coming out of this parametric down conversion source, going to stations A and B, but now A and B are not even in the same lab. They're not just removed by a few meters, but they are removed by 400 meters across the campus of Innsbruck University. And so, in order to find out how much time you have to do the setting and then the detection, you just have to find out what's the light travel time for 400 meters, and that happens to be 1.3 microseconds. So that's the time you have at your disposal. That is the time, the maximum time you have for randomly choosing a detector setting and then detecting and registering the event. Now, how do you randomly choose the detector setting? One option is to use a computer to provide random numbers, but these are in principle pseudo-random numbers, so they come out of a mathematical algorithm that is deterministic, so in principle you could predict all these random numbers, and if nature were very conspiratorial, then somehow you could still get these very high correlations. I don't know how, but okay. Now they therefore chose a physical random number generator. And the physical random number generator they chose is really very simple. It's just an LED, a light source, that just provides a stream of photons, and then you have a beam splitter. And so if you place detectors behind that beam splitter, sometimes this detector will click, sometimes that detector will click. It's just the Poisson statistics of a light source. So now, whenever the one detector clicks, you might call it a 0, and if the other detector clicks, you call it a 1, and that means you have a stream of values switching randomly between 0 and 1. So as a function of time, you would have, say, 1 for some time, then switching to the 0 value, back up to 1, and so on. And so that was their random signal, their physical random number generator. Okay. Now, one interesting aspect in all of this business is, of course, how fast is this? And the parameters they chose were such that the typical time between switching between those random values was 10 nanoseconds. So that is well within the 1.3 microseconds range. Now, how do they use this random signal? Well, in their case, they really rotate the polarization at the speed, and for that purpose, they use an electro-optic modulator. So that means they have a voltage coming in. That is the output of this random number generator. The voltage applied to this material changes the refractive index in such a way that the incoming polarization will be rotated. And the voltage just has these two binary values between the switches randomly. And so then, afterwards, you just have the signal go onto a polarizing beam splitter and analyze it. So say horizontal with respect to this axis goes to one detector and vertical goes to another detector. So that's just one detection setup. It's a two-channel setup. Well, that's the preferred version. But the point is that you are quickly rotating the setting in front of the polarizer. Okay. And so now it turns out that this whole random setting of the voltage and the detection, all of that together takes less than 100 nanoseconds. And so in this way they really close the detection. They really close what is called the locality loophole. That is the possibility that you could have a signal traveling below the speed of light between the settings. Okay. Now the detectors, unfortunately, they are not perfect either in this experiment. So let me just announce a few numbers. If you take the overall collection and detection efficiency, it's still only 5%. You get, in their particular experiment, about 10 kilohertz signal counts, so 10,000 counts per second. And you still have a dark rate, but that's only 100 hertz. Okay. Okay, so you get this random switching, you get the detectors, and then what they do is very nice. They time tag these events by using atomic clocks. So they register the precise moment of detection, and only later, after the experiment is finished, they take all the data into a computer and compare and find out, for example, what are the coincidences and what are the statistics. And so one of the nice outcomes of this experiment is you can actually download the raw data from the web. They provided it on the web, and you can try to analyze it yourself. And then you see that, for example, you first have to find out what's the actual time difference between the arrival times, because the time between the source and detection station A is not quite exactly the same as that between the source and detection station B. So you have to take these two traces, these detection traces, so to speak, and you have to find what is the correct setting. And then you also will immediately notice that, of course, since the detection efficiency is only 5%, a lot of the time you don't have coincidences. A lot of the time you lose the other particle of the pair, or maybe you lose both, but then you don't see anything. And so you can try to analyze these data yourself. So that was put up in 1998, and I guess this www.quantum.at must have been one of the first websites. I didn't check actually whether it's still there. Now, they found perfect agreement with quantum mechanics and 30 standard deviations violation. Okay. Now let me move on from these parametric down conversion experiments. One thing that is still left open here is obviously the fact that the detectors are not really that good. And so you have to make these extra assumptions that I already mentioned, that the detected pairs are a fair sample of all the pairs. And so it would be very nice to be able to close that loophole. Now, photon detectors right now are on the level of, say, 50% or so detection efficiency, which is, as we will see later, not yet quite good enough. But you can just have a look at other systems. And a system of that kind, which is really nice in terms of super high detection efficiency, are ions. So let's discuss this ion trap Bell experiment, which was done by the Vineland group in 2001. And I want to spend some more time on it because it also nicely demonstrates all the tricks and manipulations you can do for these quantum systems. Now, what is the setting? The setting is they have trapped two ions, two beryllium ions, and the way to trap these ions is well known. Since decades, you have to generate a particular configuration of oscillating electromagnetic fields, which will then provide the trapping potential. Now, the distance between these ions is only 3 micron. So it is clear from the outset that in this experiment, again, you won't be able to have space-like separation, because the time it takes light to travel 3 microns is just so very short that you don't have a chance. On the other hand, you will be able to close the detection loophole, and that we will see. Okay, now let me first draw the level scheme. What does it mean if I draw up or down for these ions? And it turns out that even if you look into the electronic ground state, so to speak, of the ion, if you look very closely, there are there's a number of different levels. And so I'm now drawing the level scheme only for these so-called ground state levels, the hyperfine levels in the ground state. And these are different spin levels, and I will label them in a minute. So there's the quantum number F, which is the really total overall spin of the ion, including the nuclear spin. Electron spin plus orbital angular momentum plus nuclear spin. And it turns out that for this particular beryllium ion, you have states with a total spin F equals 2, and if the total spin is F equals 2, there are 5 different projections of the total spin, yeah? -2, -1, 0, 1, 2. And so the state that they happen to use and call down is just the state F equals 2, MF equals -2. So the others they won't use. And you might wonder why are these energies not all degenerate? And the reason is that a magnetic field has been applied. Okay, now there is another state which is the designated up state, and that belongs to another series of levels, which is the one for F equals 1. So F equals 1, MF equals -1, and that is their so-called up state. So these two states are the ones they use, these two states are the ones that I will draw in the following. All the other states we will tend to forget. And there is a hyperfine splitting between these of about 1 gigahertz. Now, in order to prepare the states and also read out the states and so on, you need to be able to coherently induce transitions between those two states. For example, you say, I want to rotate my state from up to down or halfway in between. And so you have to couple these two levels. Now what do you do? If the energy splitting is just 1 gigahertz, that's microwave frequencies. So the natural thing to do would be to irradiate it with microwave frequencies. For example, just do like an NMR experiment with a 1 gigahertz drive. But that's actually not what is being done, because that would not have a very good spatial resolution. Yeah? These are only 3 micron apart, and if you just have an oscillating magnetic field source and don't play any tricks with magnetic field gradients, then you can't distinguish between the two ions, but you want to address them individually. So it would be much better to have a kind of beam that is less than 3 micron wide, and yet has a frequency of 1 gigahertz. Of course, that somehow doesn't work with electromagnetic radiation, and the trick is to actually use 2 laser beams with a difference frequency of 1 gigahertz. So let me explain that. Okay, so now the process I'm talking about is called stimulated Raman transitions. You have these 2 levels. Let's again call them down and up. They are separated by a gigahertz. And you want to use lasers to make a transition, so you actually illuminate it with 2 lasers, and the difference frequency is 1 gigahertz. Now the lasers, of course, they have, say, electron volt energies. And so they would actually induce a transition to a much higher lying level. And then you just make sure that with your lasers, you don't just hit directly the transition from this lower state to the upper state, because otherwise you would populate this upper state. You don't really want this. So what you do is the following. you illuminate with one laser that will take you to this dashed line. There is no level there. There's a finite detuning to the nearest level, so you don't populate that level. And then you have a second laser that takes you down again, and the difference between the laser frequencies is just 1 gigahertz. So that is nice, because now, without ever populating the intermediate state, you can have a coherent transition going between down and up. So essentially, I imagine there is a beat node between two lasers, and the beat node drives the transition. Now, okay, so, and the frequency difference between the lasers is just the energy difference. Okay, so this is one thing. That's all nice and good and could be used to control the state of an individual ion. But we also want to be able to entangle the two ions. And the question is, how do we do that? And the answer is, they are sitting in the same trap, and they have some Coulomb repulsion. So it turns out this system of two charged repelling particles in a trapping potential just has the usual normal modes of a vibrating system. And for example, if you consider only the motion along one direction, say the direction I've drawn here, then you would just have two coordinates, and that means two normal modes. One of them will have the structure of a center of mass mode, where both ions move at the same time, and the other will be the relative mode. Okay. Now, how can that be used to actually entangle the states? The trick is that the way the lasers act on the atom also depends on the position. And the reason is very simple, because it depends on the phase of the electromagnetic wave at the point of the atom. But if the atom moves, then the phase changes. So the laser transitions actually couple to the motion. And let me first explain that without yet having this two laser scheme. So for example, if I just have one ground state level and I'm going to an excited level, then the effective part of the Hamiltonian describing this laser drive would look like this. I go from the ground state to the excited state. There would be an equivalent part in the Hamiltonian where I go from the excited state to the ground state in order to have a Hermitian Hamiltonian. Now, the amplitude multiplying this will depend on the amplitude of the laser, obviously, but it also depends on the phase of the laser at the point of the atom. And so that would be e to the I. Now, I assume k is the wave number, along the direction of motion at least, multiplied with x. And x I can write as an average position, x bar, plus some small quantum fluctuations around x bar. So let me call them delta x, and I will put a hat in here to say that this is an operator that depends on my motion. And now the idea is, for example, I can expand this. I can say, this is e to the I k x bar times 1 plus I k delta x, and higher order terms. And now I see that in addition to having this transition between the electronic levels, I might also flip, or I may also change the vibrational state, because delta x acts on the vibrational state. And so delta x I could then express in terms of the normal modes in the trap. So just schematically it would be a sum, in the usual way it would be a sum over the normal modes. Okay. So it would be a weighted sum of the normal mode coordinates. And so we have here a way of changing the motional state while we at the same time also change the electronic state. Now for the two laser transitions, for those stimulated Raman transitions, it turns out that what matters here instead of k is just the difference of the wave vectors. So I could say delta k is k1 minus k2, and then that would enter this. And the way to see this is relatively simple. You have, say, one transition going up with e to the I plus I k1x, and the other transition going down, which is the Hermitian conjugate part, with e to the minus I k2x. And so then you can control this in a wide range just by changing the angle between the two laser directions. And so that will change delta k. Okay, so now we have everything that we need, because once you realize that you can change the motional state during the laser transition, there's a very clever scheme to entangle the internal state of the ions, and that was first proposed by Malmer and Sorensen. And let me briefly explain how this works. Now, I will draw a level diagram, and in this level diagram I will indicate not only the internal state of the ion, that is whether it's up or down for both ions, but I will also indicate the phonon number in the normal modes. Now there are in principle two normal modes, or even more if you count the motion in the other directions, but let me focus just on one of the particular normal modes, maybe selected by its frequency, one that is convenient. So the ground state of the system would be one where both the atoms are in their spin ground state, in the down state, and I have zero phonons. Now I can make this Raman transition to a state where, say, the first ion has flipped, or the second ion has flipped its spin. And again, somewhat similar to what I drew previously, there are just these two transition pathways. So either it's up, down, 0, or down, or either it's down, up, 0, or it's up, down, 0. Okay. Now, however, I want to exploit these other vibrational states. And so I will draw this ladder of vibrational states here, which is to say I can have not only 0 phonons, but also 1 phonon, 2 phonons, etc. Now the idea is the following. Again, I'm exploiting a transition where there is a virtual intermediate state which is a little bit detuned from the level that I would otherwise go into. So one is choosing two different laser frequencies in such a way that there will be a two-photon transition via a virtual intermediate state that is detuned by some delta. Again, the purpose of this is that the intermediate state is never really populated. You never really put a phonon inside there, but it was still important to have this matrix element present. Okay, so this transition then will take you to this two-photon transition will take you to the up zero level. That's how you arrange your laser frequencies. And there will be an equivalent two-photon transition going through the other pathway. Now, each of these transitions is characterized by some amplitude, some strength, that would be the prefactor in the Hamiltonian. And conventionally we call this capital omega. This is called the Rabi frequency of this transition and is proportional to the laser amplitude. Here again, capital omega. And the combined transition has an amplitude that can be calculated from second-order perturbation theory. So you have to multiply the two amplitudes and you divide by the detuning. And so now what you get here is you have a direct transition between the down-down state and the up-up state. All these intermediate states are only there to help you along, to go there, but they are never populated. So the effective Hamiltonian would say, oh, there's just a matrix element between down-down and up-up. The strength is given by omega squared over delta. And if you have such a Hamiltonian and you start in down-down and you wait for the appropriate time, you will have just an equal superposition of down-down and up-up. So after the appropriate time, we will have a state like up-up minus I down-down. And that's an entangled state, and so then you want to do your Bell test. Okay. Now the one thing, the crucial thing that I still have to discuss is how does the detection work? Because that was the promise, that detection is super highly efficient for these ion experiments. And so the basic scheme works like this. You arrange the situation such that you illuminate the ion, and either it glows, that is, it scatters many photons, it is bright, that is, if it's, say, in the upstate, or it's simply dark, it doesn't scatter any photons. So there is a state-dependent scattering of photons, and it's called resonance fluorescence. So let me just draw these down and up states again. Down state, you remember, was F equals 2, MF equals minus 2. Up state was F equals 1, MF equals minus 1. And then there's a higher state up here, a higher electronic level. And by illuminating with a laser at the right frequency, you can induce a transition between these levels. So what will happen is you excite it, and it falls back down, emits a photon, you excite it, it falls back down, emits a photon. That is called a cycling transition, because you go through it many, many times, and each time you go through it, you essentially scatter a photon. So you have a stream of incoming photons, and you scatter them, and you can look at the ions from the side, so to speak, and see the ion glow. Okay, and since only starting from the down state you get the cycling transition, but not starting from the up state, this is state-selective scattering. And the good thing about the scattering process is you can just scatter many, many photons. And then even if your photon detector has a relatively low efficiency, you will still be able to see many of those photons. So then there is no question to distinguish these two alternatives. And so in the experiment they did in 2001, the down state gave on average for the time during which they illuminated about 60 photons that were detected. And if you had the up state, it was dark. You don't detect photons. And so then putting all of this together, you would trap the ions, you would prepare the entangled state via this Møllmer-Sørensen gate, and then you want to detect whether your ion is up or down, but not just up or down in this basis, but with respect to an arbitrary polarizer setting, so to speak. And having an arbitrary polarizer setting, you can also implement by just rotating your spin. I mean, think of the Stern-Galler apparatus. Either you could rotate the Stern-Galler apparatus, or you could put in a little magnetic field before the spin enters the Stern-Galler apparatus and rotate the spin. So that is done in this case, and it is done by taking these stimulated Raman transitions to just rotate the spin in this down-up Hilbert space in any way you want. So you just choose a rotation angle, and after that you use this very efficient detection process. So these different polarizer settings are just implemented by rotations. And so overall, this experiment has very convincingly closed what people would call the detection loophole, that you have such low detection efficiencies in these photon experiments. All of this has been gotten rid of here. The only downside is, of course, you only have this 3 micrometer separation. So since this detection is not that fast, there would be plenty of time in principle for some mysterious signal to travel from here to there. Nevertheless, at least they take great care to point out that no known interaction, if you analyze everything we know about Coulomb interactions and so on, electromagnetic radiation, would have contributed to these correlations. So if there is such an interaction, it's something which we don't know of yet. Okay. Are there any questions? at the moment. Well, if not, see you next time.